All right, let's get started with the second problem of the day. This is going to be LeetCode number 73, set matrix zeros. Given an m by n integer matrix, if an element is 0, set its entire row and column to zeros, and you must do it in place. Okay. If an element is 0, then you set its entire row and column to zeros. You must do it in place. This seems like a DFS question at first, in terms of first impressions. I guess the main thing will be, how do we tell whether an array or a cell is an original 0 compared to a new 0? Right? Because I think the main sort of thing that screws us over here is that we are setting all these values to 0 within its row and column, but there's no really easy way to figure out whether or not a row or a column has a 0, or whether or not the 0 within any given coordinate after you do the first one is going to be an original 0, right? We could do 2 passes. We know that since, well, let's see. Each matrix, or each cell in the matrix, can be any integer. So that rules out using a placeholder integer. I think using an additional matrix, a copy of it, would be the easiest and most straightforward option, but of course that's not really so yeah. So straightforward solution is to create a copy of the matrix to keep track of where the zeros are, and then copy it back into the matrix. And that's certainly one option. But of course this would take O of m times n space, which is, as the follow-ups say, probably a bad idea. So how could we improve on this? Well, how large? Well, our dimensions are 200 by 200 maximum. One idea is that we start by iterating through the matrix and pass the columns, or fill the row / column array. The idea is that if we have a maximum of 200 by 200, we can use an array, and each cell in the array will be true or false depending on if a 0 exists on that row or column, right? Then we make a second pass through the array, and we see that given any row or column, if there is a 0 that exists on the row or column from before, then we will set our current value to 0. This then will give us, let's see, this will give us O of m plus n space, because the idea is that simply our row, let me think about this some more. This will be m plus n because we have m rows and we have n columns, and we need a space for each of them, right? So if we had a 100 by 100 grid, we need 100 rows and like 2 arrays of size 100 each. And if we had a 300 by 300, we need an array of size 300, 2 arrays of size 300 each, right? So this is an m by n space solution. And how could we break this down even further, as the follow-up suggests? Well, the follow-up suggests that we do something within constant space. How could we use constant space in this case? Well, a constant space solution would probably involve using some additional math or some additional trick within the algorithm. Let's think about this. If we truly wanted to devise an m by n, or a constant space solution rather. If we wanted to do a constant space solution, that means that we cannot store all of the zeros. We cannot store all of the zeros within there. But I mean, we don't need to store any zeros within the same row or column if we did that, right? We wouldn't need to store like each individual zero if we were doing our second approach of having the true or false Boolean array on the row and columns. We'd only need one instance of it. Though I still, I guess, disagree that that would be a constant space solution. It's a really interesting thing. I think I'm going to start by doing the m plus n space approach, and then we can start to think afterwards sort of what we might be able to do in terms of getting a proper constant space solution. So let's start by creating a row array. Will be a bool array of size matrix.size, and call array, which will also be a bool array of matrix at 0.size. And this is assuming that m and n are at least 1, which they are. So now we can iterate through the matrix, and populating, we can populate the row and call arrays. So we can do matrix.for each indexed, row index, row. And we can say for each element within the row, with our call index and our value. And we can say if value is equal to 0, because this is an array of int arrays. And then we can say that if that is true, then for our row array at our row index will be true, and our call array at our call index will also be equal to true. So now, now we can also do something within here if the value is not 0. If the value is not 0, then we can probably consider seeing if, actually no, we can't do this here, we have to do a second pass. And the reason why we have to do a second pass is that there's a chance that our zeros are actually at the bottom of the matrix. And if we do it like this, where we say that else if it exists within our array, then change it, that ends up causing a problem because we iterate and we sort of finalize the top part and the top left part of our array before we go down to the bottom right. So we need to iterate through the matrix again. This time setting values if they are on the same row column as a 0 originally. So matrix for each indexed. Very much the same thing. In fact, exactly the same thing pretty much. And hopefully Kotlin doesn't yell at us for concurrently modifying the array in this manner. I don't remember if it does so for arrays, like cells within arrays. I guess we'll just have to find out, right? So, if row at row array is equal to true, or sorry, if row array at row index is true, or call array at call index is true, then we should say that our matrix at our row index and our call index is equal to true, or is equal to 0. So the idea is that if we have a row or column that shares the same row or column as a 0, then we set that cell to 0. Pretty straightforward stuff. Otherwise, we just don't do anything. And of course, since this is a void function, we don't need to return anything at the end. So this is sort of like the straightforward approach. Let's go ahead and run the code and let's see if there are any issues with it. Looks like a bool array. Is it bool array or boolean array? Is boolean array of. Of course, we need to initialize the values. So this is a pretty straightforward solution. Looks like it passed the first case. Let's check to make sure that passes the second case. At least the second iteration of that. And let's go ahead and take a look and think about sort of how we could shrink the space of this even more, right? Because right now our row and column arrays have to be at least the size of our matrix. Even though we don't store every individual 0, we are storing at least one value for each row and one value for each column. Let's see. Perhaps there's a way to say that. Is there a way to prevent the amount of overlap on the row and columns? And can we extend that further to the point where it goes down to what is potentially constant? Actually, the more that I think about it, the more that I feel like maybe DFS wasn't the right call initially. Because if we were to, let's say that we were to say at each individual 0, we went and, first of all, we had to keep track of that 0, right? All the cells that contain zeros originally. And then we'd go through each row and each column for that 0. And we'd set all the values to 0 if they weren't already. In that case, I think that would essentially mean that we would be running this algorithm in O of m times n squared. Because potentially we would have to go through, if we had an m by n matrix filled with zeros, those would each traverse a row and column on their own. And that would produce up to, let's see, it'd be like, for the top left, we'd have to traverse m rows and then n columns. And then we do m minus 1, m minus 2, m minus 3, m minus 4. Yeah, so we'd probably do some sort of polynomial time there when it comes to traversing each row and column within. And I don't think that's efficient enough. I think we should be able to get away with an O of m by n solution on its own, no polynomial, along with a constant space. The question really then becomes, what is this constant space and how we can optimize it? Could we do it based on, what I'm thinking is maybe it's just gotta be some smarter way of storing the columns or the rows. I was originally thinking something like, maybe something involving divisibility, like if a row is, let's say that there's a 0 on a particular row and then any row that's like divisible, but I don't think that's the case. Or maybe the idea is to sacrifice some time and instead get a solution that uses a constant amount of space. That's a good question. I don't think any of the LeetCode solutions so far have been like sacrificing time for space. Let me just first make sure that this solution works first before we think about sort of like the other solutions. Yeah, so this solution works, but like, what could we do? Is there a better way of dealing with this than just tracking the rows and columns in like this sort of thing? There's gotta be. But I mean, what does constant space actually entail? Honestly, I'm not too sure. This might be one where I actually end up stopping a little bit early because, quite honestly, I'm lost. I don't have really any ideas on how I could further improve on the space complexity of this problem. It would have to do some way of storing the rows and columns in a different way that is smarter than just saying, okay, for each row we do this. But how? That is the better answer, or that is the better question to ask. And I don't think there's any just like, oh, just use this data structure instead, that will help us in this case. I don't know. I'm really hoping though that the answer isn't some sort of obscure algorithm or some sort of obscure thing to use in order to figure out the solution in constant space. But we'll see. In any case, I think I'm going to take a look at the solution and I'll be right back and to see if sort of what that constant space solution looks like, because I'm all out of ideas. Honestly, a very, very ingenious solution. I mean, looking back, it was pretty straightforward, but Man, so basically the idea is that rather than creating those the individual Boolean array for the row and the column, why don't we just use the first row and the first column of the matrix as that array? Um, and so that's what we do basically in this approach, where we go through and we check if the value is a 0, then we'll set the first row and the first column values to 0. Then when we go through the matrix the second time, we'll actually need to start by on the first row and onwards, and the first column and onwards, of course, because the first or the 0th row and the 0th column contains a flag as well as our zeros. So it would be a little bit weird, and it would be incorrect to actually go through those values at that point. Then after that, we will check additionally the 0th row and the 0th column on its own. In this case, we don't really know whether or not, because of the way that we use our flag in our first, in our original, in our 0th columns and our 0th row, we don't know if those zeros that were there before or that are there currently are actually flags or actual 0 values. In this case, what we do is that preemptively, when we do our first pass, we will check to see if the row or column is 0. And if it is a 0 in our row or column, we will set a flag. And there later on, after we've messed around with the rest of the matrix, we will go back to our 0th row and column, and we'll check. And we'll say, okay, so originally did we find any zeros in our in our 0th row and our 0th column? If yes, then we'll set those the row and the column respectively to zeros. And that's how we sort of we get that constant time space, or constant space, and O of m by n runtime. We end up sort of burying our array of checking of whether or not a 0 exists within the row or column within the matrix itself, and we had to run a little bit of additional logic to make sure that it all goes well. But in the end, it works all right. In any case, I hope you learned something, and I'll see you for the next problem.